dynamic instrumentation in contrast to static instrumentation. So by static instrumentation, I mean all the telemetry and the signals that we pre-program into our software so that later we can analyze behavior as it's running in the field and debug it and monitor it. So these are things like logs and metrics and printf statements, traces, debug pages, what have you. And the thing with static instrumentation is that by definition, when you need more of it, you need to change the source code, right? So you need one more log statement, you haven't programmed it, well, you need to go back to the source code, add one more log statement, recompile, redeploy everything, restart all your services, and then you get your new data. So now, in contrast, dynamic instrumentation refers to the capability of adding telemetry at runtime while programs are running without the need to change any source code or redeploy anything or even restart any services. And so why might you want this? Well, fundamentally, it's all about answering unanticipated questions, right? So static instrumentation is all about questions that you did anticipate, right? You wrote some code and you thought, oh, I'm not really sure, these things might go wrong. I'm going to put a bunch of metrics here and logs so that if bad things happen, then I get some data and I have like some chance of figuring out what happened, right? Well, but what if you didn't anticipate, the situation that actually happened, for example, in your production environment? And having the ability to instrument dynamically to answer unanticipated questions, it's really empowering for your curiosity, right? And being curious about the behavior of software, particularly in environments like production, it has all sorts of, great benefits. For example, it might get you written up in the New York Times if you are Andres Freund, the Postgres developer from Microsoft that discovered the XZ vulnerability, backdoor, right? And obviously, the obvious of use of dynamic instrumentation is for debugging and incident response, right? It really enables very quick iteration where you get to hypothesize about what might be happening in your production environment, collect some data to prove or disprove the hypothesis, and then based on that, ask another question to dig deeper and eventually root cause whatever is happening. So now, if you buy that dynamic instrumentation is a good thing, if you want it, the question is, well, what does it take to implement it? How do we build a tool that instruments other programs? And fundamentally, you need two things for this, right? You need the ability to basically inject codes one way or another into a running process, such that you can inject this code, you can hook into the relevant places. For example, if you want a new log line in a function, you maybe hook the beginning of that function and have it run your code and then give back control to the original function. And then this code that you injected, you wanted to do certain things, like, for example, you wanted to read memory from the target process. And not only read it, but also make sense of it, right? And then export the memory that was read to be analyzed, maybe outside of the process. And so historically, there's been tools that do these two halves, right? We've had all sorts of tools that do hooking or code injection. Maybe the original one was dtrace for Solaris at Sun. And then in the Linux world, there's been tools like SystemTap or LTTNG that let you hook all sorts of points in the kernel mostly, but also in user space, and react to events that happen and describe, do something, consume these events. In more recent times, there's been a new kind of wave of tools for Linux like BCC and BPF trace that are built on a newer technology called eBPF that we're going to talk about. There's other things like the open telemetry auto instrumentation agents for different programming languages do various types of code injection and hooking and dynamic instrumentation. And by the way, to give you an idea, this here is a BPF trace one-liner. BPF trace is maybe the tool that has gotten the most use recently. And BPF trace lets you write these little scripts. A lot of them are one-liners where you specify what event in the system you want to hook and what do you want to do, what action you want to perform when those events are produced. So for example, just to kind of get a taste, this is a BPF trace one-liner that counts how many system calls the different processes running on your system are performing. Okay, so that's for code injection. And now for reading memory of a target process and making sense of it, well, this is a big part of what debuggers have always done, right? Big part of what GDB, for example, does. And now I should say that the idea of combining these two technologies is not particularly novel. In fact, there's no clear separation between the two halves here. For example, a bunch of debuggers do some degree of code injection and code generation. And conversely, a bunch of the tools on the left do some degree of reading memory out of a target process and making sense of it. So, there's always been a lot of cross-pollination, let's say. And so now I'm going to dig a little bit into the technicalities of these two technologies. And so let's start with debuggers, right? So what do debuggers do and how do they do it? Again, a big part of what they do is that they read memory out of a target process and they decode it. They make sense of it. They extract data structures and variables. And they do this by consuming and by using debug information that is produced by compilers. And compilers emit this debug information in a standard format called dwarf for the particular use of debuggers. And dwarf has all sorts of good stuff if you're writing a debugger. For example, dwarf can describe the layout of structures. Structure types from your programming language, the layout in memory. Or dwarf can help map source code addresses to map source lines to code addresses. Dwarf can contain instructions for unwinding the stack from different points in your program. Also very relevant for us, dwarf can contain variable location lists which describe where in memory you can find variables relative to a line of code where that control flow might currently be at. So I have just a listing to illustrate this. Right? So if you can read this, that one at the top, exec statement in OpenState, it's a random function from the cockroachdb code base. And if you decode the dwarf information for this function, the dwarf information is a big tree that has all sorts of nodes. But if you look at the node called the dvtag formal parameter, you'll see that that node corresponds to the description of the variable x being the receiver of our function. And if you look at the dv@location, location, these are the locations list. So these tell you where in memory you're going to find this variable. And what this tells you is that if your execution is somewhere in between instructions at address 35BB380 and 35BB416, then you'll find your variable, which is a pointer, by the way, you'll find it in a register, in REX. And then after a few instructions, it looks like the variable is getting spilled to the stack because the next location list for the next code location tells us that we can find the variable at offset 72 relative to the frame base, the base of the stack frame for the currently executing function. Okay. So this is the sort of information that gets used by a debugger to make sense of, to read variables from memory and make sense of them, right? Now, the other big thing that the debugger does is let you place breakpoints, right? So debuggers let you interrupt the execution of a target program and give control to the debugger so that you can, well, do a bunch of stuff, for example, look through the memory of the program. And the way debuggers do this on Unix is generally through this kitchen sink type of system called ptrace that intermediates a lot of communication back and forth between the debugger and the debuggee. For example, if you want to place a breakpoint, what the debugger might do is, well, first of all, you need to figure out where you want to place your breakpoint, but then a debugger might stop the target process and replace one of the instructions in the instruction stream of that program with a software interrupt, with an int3 instruction. And so from this moment on, when the control flow reaches this instruction, the program will generate, or the CPU will basically trap into the kernel, will generate a software interrupt. And in response to that, the kernel will generate a signal that goes to the debugger while keeping the original thread suspended, blocked, right? So now the debugger is in control, your original program is stopped, and the debugger gets to do whatever, look through its memory, ask you to type some commands, And eventually, you'll want to resume the program that you've interrupted. And you do that through yet another ttrace call. You tell it ttrace continue. Right, so this is super cool, right? And you might now ask, well, why isn't this the end of the story? It seems like debuggers can, well, they can take control out of a program and then they can look through memory, they can do whatever they want. Isn't this what we were driving at with, answer unanticipated questions? And the problem is that, in practice, the way debuggers are built is not ideal, particularly for production systems or for production environments. There's a bunch of issues. One of them is that this interaction that I described here is just too slow, right? Like this kind of like ping pong of transferring control back and forth between the debugger and the debuggee is just very slow. It doesn't really fly in your production environment. We need something faster. And also, this technique is also just not safe. You can realize that when a program has been modified with these int3s in it, for example, it's now in a very fragile state, where if the debugger were to crash at this point and there's nobody around to catch the signals that were generated by that program, well, you're going to have a bad state, right? So again, not ideal for production. Which is why other tools that are in the code injection game do things differently, right? So how do these other tools work? And here there's a lot of heterogeneity. Different tools do different things. For example, there used to be, I should say, some tools that would generate kernel modules that would then load into the kernel based on the specification of what events you want to hook. And being in the kernel, they have access to various low-level events, and they can run code in response to them. Now, other tools, they do straight up, honest code injection, right? You want to write some new code in the memory space, in the address space of a target program. So you want to do stuff like, add an executable memory mapping to the virtual address space of your program, put your code in it, and once your code is in that process, you want to figure out how to hook it, how to jump to it, right? So, for example, let's say we want a log statement somewhere around this instruction or the line of code that corresponds to this instruction. Well, what we might do is we might replace one instruction or maybe a couple of consecutive instructions with a jump that's going to jump to the code that we injected, right? So now we've basically hooked this function. And what does this code do? Well, whatever we want, it's going to do our bidding. But in practice, you want it to do stuff like, well, read some memory. So maybe you want to allocate some buffers on a stack, copy over some memory. Then maybe you want to exfiltrate that memory that you've read out of the process as quickly as possible. So maybe you want to write it to a socket or something like that as quickly as possible. And then eventually you want to transfer control back, right? Because you don't want to affect the execution of this guy. So in order to do that, you have to now simulate the instruction that you've replaced, which can be a whole thing, right? Because the effects of instructions can actually be dependent on the position, on the address of that instruction, right? For example, if they're using position relative memory addressing on x86. But if you figure out how to simulate the effects of the instructions that you've replaced, then you simulate them and you basically jump back, right? And then this function is none the wiser. So there's all sorts of kind of technical details and arcane details here that you need to work through, but people do it. And then yet another option that you have for code injection, a more modern option, is eBPF uprobe. So I'm going to talk about eBPF in the next slide, but for now, just know that eBPF uprobes are a way to ask the kernel to run a program that you specify, so an arbitrary program, whenever execution reaches a particular address in user space, in a user space binary or maybe a shared library, right? So by having the kernel be in charge, the kernel gives us a lot of nice things. So the way these uprobes are actually implemented is that the kernel goes, just like a debugger, it replaces one instruction with an int3. And now the kernel is in charge of remembering the association between the programs that are supposed to be attached to that address and the address, right? So whenever execution gets to that int3, the kernel knows that it needs to run all the eBPF programs that were attached to it, right? And the kernel is also now in charge of simulating that instruction that it replaced. And it's all safe because, well, because the kernel deals with it. The kernel makes it such that there's nothing, for example, that can crash in such a way that, you know, this program is affected, right? So the kind of hooking that is done by writing this int3 is completely transparent to the target process. And so eBPF uprobes are super cool. Side-eye, for what it's worth, our product kind of does both. We use eBPF uprobes, but we're also kind of working on more native, more low-level code injection. And for reasons that I'm going to describe briefly, but actually my partner Andrew is giving a talk in New York next week at Phil's series of talks. So if you want to hear more, come to New York next week. Yeah. But eBPF, super cool technology. So I thought I would talk a little bit about it because it's really foundational for all sorts of tools these days. So I'm actually curious. This technology is in the zeitgeist, but I think not that many people perhaps understand it well. So maybe we can do a show of hands. How many people will say they understand what eBPF is about? Okay, so some, not that many. So I'll say a few things to kind of get us on the same page, right? What is eBPF? Well, it's a technology, technology developed in the Linux kernel that lets you attach fairly arbitrary programs called eBPF programs to all sorts of hooks in the kernel. For example, you can attach these programs to hooks in the networking layer. So you can intercept network packets and perhaps make routing decisions. You can attach eBPF programs to LSM hooks, to Linux security module hooks, to implement security policies. You can attach them to kprobes, which basically means that you can attach an eBPF program to any instruction address in the kernel. You can hijack kernel execution for tracing purposes, for example. And as of, this is hot off the press, but as of very recently, the latest Linux kernel version, you can also attach them to hooks in the Linux scheduler. So you can affect scheduling decisions between processes through eBPF programs. And then there's also this weird thing called uprobes, which is what I've described before. So you can also ask the kernel to attach an eBPF program to any address in a user space program or shared library. So that's what you can do with it, with eBPF. But what is it? Well, it's a combination of a few things, right? First of all, it's an instruction set and a backend for Clang and GCC. Right, so you can ask Clang to compile your C program to eBPF. And then it's a verifier, a static verifier for programs in the kernel. So when you hand a BPF program to the kernel actually verifies that program is safe, meaning it does not perform any sort of out-of-bounds memory accesses or dereference bad pointers. And it also verifies that your program will finish in a finite number of instructions. There's also a JIT, a just-in-time compiler for BPF in the kernel, which compiles these programs to native code for your CPU architecture, and also a set of data structures for inter-process communication, such that BPF programs can, produce data that is then consumed from user space, from the outside world. And so, is this perfect? Are eBPF uprobes all we need for dynamic instrumentation? Well, you can go pretty far with them, but they do have some problems. The first one is the security model. So in order to do anything with eBPF, you need to be root. You need elevated privileges. You need a certain capability. Then there's a bunch of performance problems. Tapping into the kernel is slow, right? So I showed that the uprobes, they're implemented with a software interrupt, with an int3 instruction, right? So that is slower than, first of all, I should say it's much faster than what a debugger does, but it's still slower than just a native function call or a direct jump. So a little slow. And then reading memory from an eBPF program is also slow. So if you're inside a program, an eBPF program, and you want to read memory out of your host, out of the memory space of the program that you're attached to, you again have to go through the kernel. You do this through a kernel helper, which actually walks the page tables of the process to verify that the address that you're trying to dereference is a valid virtual memory address for that target process. So this is very different from how native memory access works, which is optimistic, right? You tell the CPU you want to load for some address, and you kind of assume that it all work out. And if that address proves to be an invalid virtual memory address, then the CPU will trap into the kernel, which will crash your program or generate a signal. Or in any case, there's a whole kind of out-of-band mechanism for dealing with faults, but not so in eBPF. And then also this verifier that I was telling you about that verifies that your programs are safe is kind of finicky. You might have to really work at convincing you that your code is in fact correct. And it's Linux only. So if you want a tool that works on your Macs, this is not it, right? All right. So let's now go back to reading the memory part, right? Let's say we have a way to inject our code. We want that code to read some memory. What does that look like, right? So far we kind of talked about it generically, but this is a concrete example, right? So let's say we have a function f that takes a foo as an argument, where a foo is a structure type defined there, right? And in particular, it's a structure type that has a couple of pointers some of its fields have pointers, right? So now imagine that we want a probe that captures such a foo whenever f runs, right? So what does this probe need to do? And when I say that we want to capture this foo, this variable, I mean we want to capture it in depth, like recursively. We want to actually chase all the pointers and read what's on the other side of the pointer and do this recursively, maybe up to some depth level so you don't, chase through the whole heap. And by the way, this is a listing of the dwarf information for this structure. We can see that this enumerates all the fields of the structure, and for each field, we know the type of that field and the offset of that field within the struct, which is very important for us, right? So, for example, the field called B is at offset 24 from the start of a foo. All right, so let's say we want to read such a foo. So, what does that mean? What do we need to do? Well, first of all, we need to start from knowing where foo is, right? Let's say that we placed our probe at the beginning of f. So our argument is maybe in a set of registers or maybe in the stack, right? And that's where the location lists from dwarf come in. Whoever writes this code or generates this code starts from knowing where that variable is, right? And once you know where it is, you want to read it, right? And namely, you want to read 56 bytes because the size of foo is 56, right? So you start by copying 56 bytes into a buffer. And then you start going through the fields and chasing the pointers, right? So the first thing, let's say the first field is a string, right? The data for the string is not inside foo, right? Foo only has a pointer to the data. The data is somewhere on the heap. So in Go, a string is a pair, it's a length and a pointer to the data, right? So our code needs to know that the length of the string is at offset 0 in our buffer, and the data, or the pointer to the data is offset 8, so it needs to dereference the pointer at offset 8 and read len bytes, right? And then kind of similarly for Q, which is a pointer to a baz, right? We have a pointer somewhere at some offset in our buffer, we need to read 16 bytes or 8 bytes for it. And then when we get to that interface, the iFace field, that's actually trickier because we actually don't know the type that's hiding inside that interface. Interfaces in Go are kind of like fat pointers. They're a pair of pointers. The first one is a pointer to a type descriptor that identifies the type that's currently inside that interface box. And the second pointer is an actual pointer to the data, right? So our code needs a level of indirection here where we read the type descriptor, we figure out the details of the type that's actually in that box, and then we run code specifically for that type, right? So this is kind of the code that we want to get to if our probe wants to read a structure, basically. And so how do you get this code? Because, you know, users are not writing it by hand. You kind of want a tool to generate this code based on the specification of, oh, I want you to read the argument whenever f is called. Well, you know, there's probably many ways to do it. The way we do it is you generate a subprogram for every type that you might want to read, right? And this program, this subprogram, this subroutine encodes the layout of that type, the total size of the type, and the locations of the pointers within the type, right? And the whole machinery is driven by one big queue where pointers are enqueued onto it and eventually read, and we kind of, through this queue, we do a breadth first search kind of exploration of the structure that we're trying to read. And by the way, and the start of it all, again, it comes from the location list, right? That provides the root of what goes into this queue of pointers that we then kind of dequeue and read one by one. All right, and I'll show you one more thing. So far we kind of discussed relatively simple probes. There were probes that attach to one particular function and read variables that are in scope for that one function. But what about probes that are maybe more expansive in scope? For example, SideEye, it has this notion of capturing snapshots of whole processes, or in fact, snapshots of distributed systems that are made out of multiple processes. And these snapshots, they have information. A process snapshot consists of information on all the threads of execution in that process. These include threads that are running on CPU at the time when the probe fires, and also all the other blocked threads. Right? And what I have here in the screenshot, I don't know if you can read it very well, but this is this is a screenshot of a stack of one of these threads coming from a snapshot. And the point that this is trying to make is that it's very satisfying to see variables at multiple levels of the stack all in one screenshot, all at a glance, right? Because it can give you a lot of information about the state of execution of some threads at the moment when the snapshot was taken. So for example, this is a thread in CockroachDB that was executing a query, right? CockroachDB SQL database is executing a SQL query. And so you might look at a very high-level frame where you might see the user that issued that query, right? And then a couple of frames down, you might see the actual SQL query that is being executed. And then a couple of frames down still, in fact, here I guess it's more like 70 frames down, you see that this thread is blocked on performing an RPC call, a remote procedure call to another server, right? And because we read the network address, the remote peer on that network connection, plus some other gRPC metadata, we're actually able to link between this client-side thread and the server-side thread that's currently handling this request, right? So the point is, these snapshots, they come from kind of more general probes, and they're useful, right? So what does it take to collect all this information? What does the probe need to do, in addition to what it was doing at the level of a function? Well, and the answer is it needs to do a couple more things. It needs to start by iterating through all the threads of execution. So in the case of Go, threads are Go routines, and the Go runtime maintains information on all the active Go routines in an array somewhere in memory. So you start by iterating through those. Then for each thread, you need to walk its stack kind of frame by frame. And as you're walking the stack, you need to recognize the functions for which you want to collect some variables. And if you do recognize the function, then we're kind of doing the sort of stuff that we did before. We start, collecting those variables recursively. But with a twist that now, so kind of in our probes before, we always knew the program counter to which the probe is attached, right? So we needed to know how to find the variables relative to a fixed program counter. But here, when you're walking stacks, right, you might find the same function on some frames. You might find it at this line of code. At other frames, you might find it at this other line of code. So you need to know how to find the variables kind of for all possible program counters. And in fact, for some of them, some of the variables might not exist anymore. So then you cannot read them, right? But if you deal with all this, then you can get a probe that it doesn't even feel like, when you say the word probe, you're thinking of like a fairly small localized thing, but such a probe can actually give you all sorts of data, right? So the moral of the story is that if you have code on the inside, if you're able to kind of inject code into a process, well, then that code can really do your bidding. The sky's the limit. You can collect whatever you want. And I think that's all I have. Kind of the idea was to show you what goes into these tools a little bit. And thank you very much for listening.
Very much, Andrei. Now we have time for Q&A. First question.
Are you breaking forwards of CFI every process you do this in?
Am I breaking what, sorry?
Control flow integrity and maybe RWS.
I'm not sure. So you're thinking about like shadow stacks, for example?
Yeah, or like signed pointers on the way forward and then branch target identification on the way back. Probably on the right side.
I am not sure, to be honest. I mean, definitely not when we're using BPF for the probes, because, well, then it's kind of BPF's problem to not break those, to be completely transparent. When we run our own code, we haven't run into this yet, but yeah, when shadow stacks, for example, are in use, we might need to kind of also keep the shadow stack in sync with our, the stack that we hijacked. So we might run into this sort of stuff. I'm not sure yet.
So how are you actually triggering when to do a snapshot? Are you still doing injecting basically the in3 with a debugger, or are you doing the replace with agent to inject code in order to start this procedure?
Yeah, well, so there's multiple ways to do it. Sometimes you do it on a timer. You say I want a snapshot a second for the next 10 seconds, or you actually do it from the outside. The user comes to a UI and says, now collect a snapshot. But you can also imagine, we haven't really built this yet, but you can imagine, triggering the snapshot in response to some alert or in response to something that happens in the process. Say, oh, whenever this error over here is generated, so basically whenever this line of code that generates an error runs, give me a snapshot of everything because I really can't figure this out, so I need as much data as I can get.
I also have a question about in order to iterate through our routines, work is going to say, oh, this variable is in this register, but that register will be up on a different thread, right? So you also have to stop every thread and type all the registers somehow?
Well, so if the thread about whose stack we're talking is already stopped, then you have its registers kind of already saved by the Go machinery that parks threads. So we can read those registers from the runtime's copy of them. And basically when we take snapshots, actually all threads are stopped because we start by stopping them. We don't need to, or at least we don't need to stop all of them at once. But yeah, when you basically cannot walk the stack of a thread that's running. So at least one by one, you have to stop them, and only then can you walk that stack.
What's the rough order of magnitude performance cost for a no-op eBPF probe?
It's maybe a microsecond.
I know that there's a separate line of work that tries to do binary software updates, basically hot reloading on binary code. Does this take any inspirations from that, or are there any connections with that literature?
Wait, can you say the first part again?
There's some work on trying to do dynamic software updates on running code without stopping it. It's like hot reloading for binary.
Are you talking about specifically kernel hot patching? I think Oracle does something, sells that and cannot.
There are a lot of these different ones, but they're mostly niche and like unique in some cases.
Yeah, there's been no inspiration from that yet. There is some commonality, right? They also need to modify codes also as it's running. But then they actually need to go further and they actually need to, well, diff the old code and the new code and come up with like a patch. So no, I would say, no, that hasn't been, I think, yet. We don't do this diffing stuff. On the other hand, we're in the code generation business to generate these probes that read and make sense of memory.